next speaker is James Posey. He is the team lead for the Applied Research Team in the Division of TB Elimination at CDC. And he's going to be talking to us, giving some information about pipeline thresholds for the integrated analytic pipeline that's included as part of ReeSeq TB.
All right, thank you, Angela. Actually, I'm not using the standard CDC blue slides today, so we're actually get to use a little bit more creative, the red and grayish black from ReeSeq TB. So hopefully I won't get in trouble. Yeah, that's my job. So what I would like to talk a little bit about today is we're trying to be a little bit more transparent in what we've been doing in the ReeSeq TB platform. Rick will go in more details later about the overall architecture of the platform, but what I'm going to concentrate about today is the upfront part. So when we started this project, the first thing we wanted to do was develop a unified bioinformatic pipeline in which we're going to analyze all of the whole genome sequencing data through the same pipeline. And this is just a simple schematic here, and I'll go in more details later. But what we're doing is we want to aggregate, as Daniela mentioned, really highly curated whole genome sequencing data with phenotypic DST data and any clinical data that we can get with these isolates all into one single place. So what we're starting with initially is mostly Illumina whole genome sequencing data. And this is just, like I said, a simplified version of the pipeline. So basically, we're starting with WGS data. And we'll go through some type of QC check, and then we'll eventually go into some mapping, variant calling. And after we get the variant calling, we'll basically be doing some annotation, and that data will eventually form probably 3 or 4 different reports that we generate. From those reports, the data then is mapped into the ReeSeq TB platform, which is then combined with the phenotypic DST data and any clinical data that's available on those strains. I don't expect you guys to be able to read all this. I'm going to zoom in on a few areas and concentrate. It's very difficult to not give a very technical talk when you're talking about pipelines and thresholds. So I'm going to try to make this as, not so technical as much as I can. But basically, this pipeline is a derivative of what's been previously published by Stefan's group a few years ago with the PHI-RES project. So we basically used that pipeline as a backbone and have modified and tweaked it or some different areas to kind of meet our needs. So basically what we're starting with, if you look at the top, is basically the Illumina reads are processed, and eventually once they're processed go through a bunch of QCs. And what you're going to see a lot of times in the maps are the red areas. Okay. All right, the red areas and also the yellow where there's QC checks that we have put in place. So we put a lot of checks and balances in place. And if anything fails one of these QCs, actually the data is quarantined and we can go back and look at it later. But as it keeps passing each of these QCs, it keeps feeding through the pipeline, and then it goes into read mapping and SNP calling. Here, basically, you're just going to we're doing reference guided assemblies, and once they're assembled, we got to do the variant call. And basically, after a variant call, we can't just stop there because we have to annotate because it's raw data at that point. And once it goes through the annotation where we can actually identify what genes are mutated, what is the amino acid change, if it's synonymous versus non-synonymous, and all that data, and we do a lot of filtering. That data is finally, at the end, mapped into the ReeSeq TB platform and combined with all the other existing data on those isolates. So what I want to do now is go a little bit more in detail, because I know there's been questions not only to critical path and others, exactly what are we doing, how are we doing the analysis. And so this is kind of where we're going to be transparent. We're in the process of putting all this into a manuscript, too, that will be published. There's some key steps in this pipeline that we had to build in place. We had to make sure that the data we were inputting into this was clean as possible and it met all the QC checks up front. We actually had to make sure we were actually sequencing MTB complex, or mycobacterium tuberculosis. Many people who know who do sequencing, we can end up with some contamination, whether it's human or normal skin flora, MAC, and other NTMs within our samples. So we wanted to make sure we put checks in there for that, because it can affect your variant calls and be misleading. We also had to do a lot of remapping and refinement to prevent any false calls. Then we do the variant calling on top of that, and eventually, again, like I said, it's annotated and fed into the ReeSeq TB platform. And we're also looking at lineage, so we can look at some of the diversity across the whole data set. Whoa. So for the input, the first thing we're starting with are what I call FASTQ files. These are some of the raw sequencing files that are coming off of the Illumina platform. And all the data we've looked at today has just been Illumina based. And we're getting a lot of the data now from NCBI through the SRA, through contributors, Stefan's group, Derek Crook's groups, and others. So the first step is to make sure it is actually a FASTQ file, because that's what's going to feed into the pipeline. And what we're doing for that is using basically what's called FASTQ validator. And basically, when you look at a FASTQ file, if you ever open it, it's just a text file, but you got to make sure the headers are there, the DNA sequence is there, and what we look at, the quality scores are there. If all those are present, then it'll pass this validation and actually move forward into the pipeline. What I'm going to be talking about moving forward, a lot of what are called quality scores, and I thought, one slide's out of order, I thought I should kind of define what some of these terms mean. So when you hear people talk about their quality scores and they're talking about, oh, that's a Q10, Q20, Q30, Q40, what does that really mean? Well, a lot of it's based off of the Fred scoring as it was in Sanger, and it's the AC's basic, the computer language within the file, and it's whether it's I'm not going into too many details, but you can convert that into numbers, numeric values. So Q10 is basically you're at a 90% accuracy, Q20 at 99%, Q30, 99.9, and so on. And so when I'm talking about these Q scores, you can see what kind of accuracy that we've set in different areas. So when you're doing sequences, we all know that towards the end of your reads, you're starting to get some poor quality, and the quality starts falling off in the signal. So the first thing we need to do is trim back the DNA sequence to basically make sure it's high quality. But also we're getting rid of any vector or adapters or anything else that could be present in the sequencing. And we're using PrinSeq here. I'm not going to name every version we're using, because what we're doing is basically trying to do version control on everything that we're doing. So now we've locked in the pipeline. It was version 1.0 with this, these different versions of each single piece. So the pipeline is just basically accumulation of multiple pieces of software kind of thread together. So what we're doing here is just using a rolling size window, looking at an average of Q20, so we're looking at 99% accuracy. Anything that falls below that is trimmed back, and then we can perform a QC report and look at what is our average read links. After we do that, and we know it's a FASTQ file, we've trimmed the data now, the question is, what did we actually sequence? Well, we hope it's MTB complex, but as again, contamination can be a problem. So we actually have to do, we do a species specificity check, and to do this, we actually do Kraken. Kraken was designed really to look at metagenomic data, but it's a real good tool to actually look at contamination within your sample. It uses what's called a K-MERD approach. K-MERD is just a string of characters, in this case 31 nucleotides. And what it looks at is signatures of those 31 nucleotides down to your lowest taxonomic group. So you can go from family, genus, species. And what we've set a threshold here is that within Kraken, that the reads have to be greater than 90% at the MTB complex level. If they're lower than that, then we have to look at see what the contamination is. Can we clean up that data, then actually remap everything? This is a typical output of Kraken. What I've highlighted here in red is the MTB complex, and you see it was at 85%. So we quarantine this data. It would just stop at that point, generate a report, and give us this information, and we know it failed Kraken. If you look at the very, very top line, you'll see unclassified reads at 12%. What that means is basically 12% of your reads, the K-MERDs, were not found in this database, and this is a Kraken database, which is bacteria and archaea and virus. So if it were human, it would be called unclassified, or if it was something that was never sequenced, unclassified. So the question is that still vector contamination, human contamination, fungal contamination, and we can blast those reads to see if we can identify what they are. And if we can do that, then we can basically rip out the reads that aren't mapping and keep moving forward. Once it's past Kraken, it keeps going into then we have to actually do a mapping. And this is now we're doing reference guided mapping versus de novo mapping. And we're using H37RV, the V3, version 3 of the annotated genome as our reference. What we're using for mapping is BWA, which is a Burroughs-Wheeler alignment tool, the MIM version. And we also use QualiMap to actually go in and look at the quality of the mapping and improve that. Once it's mapped, we have to look at the reads that are what are called duplicate reads, because in the library prep, yours is a PCR step, so you can get duplication of different reads, which can affect some of your depth of coverage and also other issues, so you want to remove those. And we also, has been shown not only what Stefan's published, but many people have published, if you go back and use GATK, which is another program from the Broad, that you can actually recalibrate around indels and also SNPs to actually make sure those are true and prevent false positives. So that's also done around any areas of that nature. And this is done with 3 different tools. We use Picard for removing the duplicates, GATK for going in and basically cleaning the indels and the recalibration. And we're also got some custom scripts that we built throughout this here, because we want to look at what is the average coverage not only across the whole genome, because we have to set thresholds there. We really haven't come up with a hard threshold, but those are the decisions that will have to be made hopefully later on Thursday, Friday, when the ReeSeq TB expert panels meet face to face. But we also not only look at the average coverage of the whole genome, but we look at the average coverage of the drug-resistant loci. And there's like 40 different loci. So we want to make sure nothing's overrepresented or underrepresented in those areas. Because if in the RS or RL regions, which are basically your 16S or 23S, if you start seeing double, triple coverage there, then it also tells you may have contamination. So we had to put in a couple of more filters. So after you have your assemblies, we basically need to go inside of those assemblies and identify where are the differences in our strain compared back to that reference strain, and then be able to give them quality scores and determine if they're true or not true. And we can use basically SAMS, what's called SAMS tools or BCF tools. And we've set these are thresholds we've set. Most of these are kind of default settings, but you can change them a little bit. So for our minimum base quality, again, we're using Q20, which is 99%. Minimum mapping quality is a Q20. And here we set a minimum read depth of 10x. Most of the strains we sequence are way higher than that. That's just a very low level. It was a cutoff. And if anything that's below that, we definitely don't want to use. And there we do have windows that we look at to make sure, because we look at the coverage report. Coverage is very important, especially around drug resistance, when we want to start looking at heteroresistance. There's been quite a bit of discussion. What is the magic number of coverage that we need? And it all depends on how low you think you want to get with your heteroresistance. And these are some couple of things that we're going to have to come to a consensus to end of the week, because we do have a wide spectrum of coverage across some of these strains. We'd also looked at SNP clusters. Typically, these can happen at insertion elements and other places where you have more than 3 SNPs within 10 base pairs of each other. We flagged that also. Typically, if you do have block substitutions, they happen in 2 nucleotides, and we flag those where we can go back and look at them. Another thing that can happen with multiple substitutions next to each other, or whether they're phased or non-phased, and looking at heteroresistance. So there's quite a, some flags we got in place where we have to go in and manually look at the alignments and the percentages to rule those out. At the end of this point, you're left with a unannotated variant call file, VCF file. What it does list is chromosomal positions where nucleotide changes were found. It tells you what your reference call was versus your alternate call, gives you quality scores. But a lot of the information is really bad here within a lot of the language, like your depth of coverage, your gene that was affected, and other information that we really need that can be mapped back easily to the ReeSeq TB platform. And to really get that information out and annotate this, we have to run it through a different part of the pipeline, and this is going through the filtering and the annotation. So for the filtering, Sebastian had actually created a list of about, I think, 400 genes that we knew are problematic when it comes to reference-guided assemblies. These are the PEPEs, PGRS genes, transposable elements, genes that have more than 50 base pair repeats somewhere else in the genome. So basically, all the SNPs that are found in those first 400 genes or areas are actually eliminated from the variant call file initially, because we know it's not very reliable in that area. So now we're left with a filtered VCF that then is fully annotated, because once we do the annotation, we use SNPF to tell us what genes affected, or is it intergenic region. It also pulls out the depth of coverage, what percent of the reads mapped to the alternate allele, and was it synonymous versus non-synonymous. And that is the information then that is mapped into the ReeSeq TB platform. So what I've highlighted here in the 2 red boxes are just some of the amino acid changes. So you'll see a reference amino acid versus alternate amino acid, and also you'll list the gene. We have the chromosomal position, we have the depth of coverage, what percent reads map to alternate versus reference, and also the quality. All that information now is captured into the ReeSeq TB platform in case we want to do more filtering on the back end. So this information is along with a lineage report, because we're using these SNPs that are defined lineages from the Cole paper. I think it's about 62 different SNPs across the chromosome to define what lineage does that belong to. In this case, this was a lineage number 1, which is Indo-Oceanic, and it belonged to the sublineage 1.1.2. That information is also mapped into the ReeSeq TB platform. What we have seen, though, is some have almost all the SNPs, kind of equalizes the SNPs out. Because remember, comparing to H37RV, so they're H37RV-like strains. And when you map them on a phylogenetic tree, they map very close to the H37RV, so it can't call the lineage because it doesn't have any of the SNPs in comparison to HR37RV. And so we just call those right now Euro-American. So what have we done up to this point? So far, we've analyzed over 3,700 strains. Basically, 3,570 have passed all of the QC filters and generated the VCFs, which have been mapped to the ReeSeq TB platform. We had 147 that have failed at one stage or another throughout the process at the QC level. Many of these were due to crack in specificity. So within the reads, they were contaminated with something else. We can go back and look at those and see if we can clean them up and actually salvage that data. We also early on started noticing that even though they passed crack in, we started seeing a ton of mutations in RRS and RRL within the same read set. And what it was a distantly related contaminant bacteria that only the RRS, RRL reads were mapping. So you got maybe 10 SNPs in these areas. And so we kind of flagged those and see if we can clean up that data set. And then we had only 4 so far that were mixed infections. So they had multiple lineages present within the sample, which we could expect in some of these areas. And so you had a lot of hetero SNPs throughout the whole thing. You may end up, typically you're at 800 to, you can go all the way up to 2,000 SNPs. Some of these were well above that because most of them were at 30 to 40% because you had mixed strains. Since we are developing a lineage report here, we can look at across that whole set, what percent of each strains are in the lineage. As you can see here in the red is the Euro-American, so a little bit over 50% of the strains we have today are Euro-American, 20 or so percent in East Africa and India. We have some in East Asia, about 15 to 20%. Indo-Oceanic, we've got about 10%, and very little in the M. africanum, which is West Africa 1 and 2, and a few M. bovis strains. So we can look at the lineage distributions, but what also I did was take some of the data that was in there, about 1,500 strains, and build a phylogenetic map over using a WG whole genome MLST, so we can look at the phylogenetic diversity also within here. So basically, this is just showing your lineages, but also showing their basically allele calls over about 3,500, 3,800 alleles, and build a UPGMA tree, phylogenetic tree, using a similarity matrix. And going from, I don't know, about 7 o'clock is your bovis, then you got your East Asian in blue, yellow is East African, India, red is your American, then you come over to your Indo-Oceanic. We have 1 West African L5 in this data set, and a couple of L6s. So this is basically showing your phylogenetic diversity within that collection. This is not part of the pipeline. This was a separate pipeline we used. I just want to kind of get an idea of what the diversity was. And you can see some clusters throughout there. So we know there's some MDR clusters that was in this data set anyway from the information that we were getting. And if you look at the resistance, even though the majority of the strains are Euro-American, most of the resistance is found in East Asian lineage, which what we would expect. So you're starting from, you got like PZA susceptible, then PZA resistance, and you'll see the distribution. Every other one's resistance. The blue comes up, which is your East Asian, who has the highest percentage of the resistance in each of those drugs. So to summarize this, we basically have developed a unified pipeline. We're on version 1.0. We've made some tweaks to the FiRes pipeline and put in some custom scripts. When I say we, I mean Matthew, who is the lead bioinformatician on this project. We've ran over 3,500 strains in there. That data has been fed into the ReeSeq TB platform. We've set all the thresholds. There are some consensus that need to be had that probably towards the end of the week when we have the ReeSeq TB face-to-face meeting. We have about 10 questions we need to make sure we are all at a consensus. I do not want to have to reanalyze all this data again. And then when we lock those in, we can move forward with the next set of isolates that will be feeding into there. And like I said, all this has been validated too. We did phi-res, direct comparison to phi-res and to some Sanger sequencing to actually validate this pipeline. So thank you. I think that's it. There we go.